Hello, everyone. Welcome to the talk on geometric scene in Olympiad geometry. I'm Shenghui. I work for Wolfram Alpha for localization system and scientific systems. During my work and my hobby, I actually use Wolfram language a lot in various kind of research. And one of them is Euclidean geometry. And I'm also very interested in some advanced topics in geometry on different level of math context. So, I also contribute quite often on the community. So if you are new to Mathematica or you have been using community for a while, I sometimes just write articles based on interesting math problems and solve that step by step with the Wolfram language. And then publish on the community to share that with all the enthusiasts and hobbyists or even advanced users to see how to use Wolfram language in solving these practical problems. Also, I feel this is a quite interesting experience for me to see how this very powerful platform to interact with some real-world contest problems and how to take advantage of the platform to help me understand a lot better of those hard problems. Even for some IMO level problems, it's Wolfram language is very powerful to visualize it and to analyze everything inside step by step. Okay, let's start the presentation. Okay, this is just a little bit background of myself and how I find those problems will be discussed in today's talk. One of the websites I use very often is Sharygin, as here. It's a very nice website that curated a lot of competition level Olympiad problems. The other one is Titu's book. Titu Andrescu, I think he used to be the chairman of American Math Society, and he has many interesting textbooks about geometry and all kinds of topics. One of them is complex number from A to Z. So this is a book I think is very friendly to newcomers and to advance the math Olympiad competitors. So it builds up from very simple complex number to geometric topics. So I also use that to test Wolfram language ability on those interesting problems. The other one is Michael Penn's YouTube channel. So this is instructor from Randolph College, and two of the problem I'm going to show today is from his video, and I think his video is getting very popular right now, like 80K views on the one Italian math problem I'm going to talk later, and the other is a very relaxing geometry problem. I'm going to show that in one of my blog posts. And he also has a collection of nice problems here. And I think that's a very good resource to learn. And I kind of use Wolfram language as my homework to practice a lot of the problem solving skills based on his instruction. So yeah, let's start to see the real world problems. And I'm going to show how to use the very specific function in Wolfram language called GeometricScene and triangle construct to tackle these geometry problems. First, let me just quickly summarize the features I feel advantage over synthetic geometry tools inside Wolfram language over kind of CAD or GeoGebra. CAD is kind of generic for like computer-aided design. So usually you have a blueprint that you point points and connect dots and do the problem solving. So GeometricScene is kind of different from that. It is a lot like what you see is what you get. I won't say the visualized part, but more about the how you code the geometric scene based on a given problem. It's basically just like you type the natural language input in a slightly modified way, so that the geometric scene will automatically give you a setup, and then you use a random instance to create a configuration based on the possible result that is satisfying all the conditions. So the code is very similar to the problems you see in the contest or traditional Euclidean geometry book. So you don't really need to understand Wolfram language to a very, very deep level. It's just very self-explanatory. The third one is very important, is like the triangle construct and the triangle center function. So these two functions give really good shortcut to create CVNs and centers. For example, I want to create an in-center of a triangle. So I think in GeoGebra, you need to just follow definition and create three angular bisectors first, and the concurrency is the in-center, right? But if you have like a large configuration, you need to do that many times. So that's kind of tedious to do that in GeoGebra. In triangle construct, you basically give it a triangle and say, I want this one. I want an in-center or a circumcenter. So you can automatically do that. And it gives you both numerical value and symbolic value. So that's really, really easy to use. And the geometric scene is also like equation solver. This will be seen in the first example in the problem in my problem list. So if you are given some quite a complicated configuration, and you are told that some of the angles inside or segments are of the same value, or some are like trisector angle. So this usually very hard to do in the CAD-like software, which is more like you do that with straight edge and a compass, so the kind of traditional way. But they are great at projective properties. Like for example, you have 4 points on circle, and their inscribed angles are the same. It's quite a famous property. But because regardless the position of the 4 points on the circle, it always satisfies this condition. So with the CAD-like thing, you just draw a random circle and put random points on that. Probably be easy. But if I specify, the angle must be some degree, or there's some like segmentation requirements for that, it's hard to put this kind of constraints in GeoGebra. So this is something I feel like geometric scene plays a really, really important role and big roles in solving this type of problems. And finally, if you analyze the problem carefully and you find out, oh, okay, I understand the conditions, every step of that, you can work with that with animation or typically manipulate functions. So that will give you very good control of generating a random or a continuously changing configuration. For example, just like a 9-point circle. So this is an example from the demonstration web page. So it works, everything works perfectly together. So you don't need to worry too much about, if this is like isolated island in Wolfram language. It does not work with other things, but it's not true. It just works with all the basic functions. Yeah, just typically in working with this thing, you just don't need to understand the Wolfram language too much. Okay. Now let's take a look at some examples from the real contest. Okay. So let ABC be a triangle such that AB equal to 9 and AC equal to 7. And let D be the midpoint of segment BC. let x be a point on segment AB such that dx is perpendicular to AB, and let y be a point on segment AC such that dy is perpendicular to AC. So if AX equal to 6, what's the length of AY? Okay, typically for this problem, you can, for example, draw, if you work with GeoGebra, you can probably draw a line with AB equal to given length and AC is on a circle. So this radius is like 7. And then the hard part is how do you just draw everything, you know, satisfy the following three conditions at the same time. So once D is the midpoint, and the other is like the two perpendicular conditions. So this is usually very, very tricky to do that if you do not compute the result before you draw everything. But in GeometricScene, you don't have to. It works just like a translation machine. You have like Euclidean distance, and the midpoint is like telling D is midpoint of BC. And X and Y are a point between the two endpoints of segment AB and AC. And then I have a geometric assertion that is going to give the confinements of points, object relations. Sometimes points, or sometimes lines or circles. So you can do that with geometric assertion. And then finally, it's given that AX equal to 6, you can use Euclidean distance AX equal to 6. So this gives you all the sort of a list of conditions that works as the basic description, same as the original problem. And then because the C, D, X, Y are unknown, so you give it a random instance for it to solve it. So for example, let me just quickly bring up the documents for that. So this is exactly, even in like a new problem, it works exactly like the basic examples in GeometricScene. So I used, in my example, I used the third template. So given some points, and then given a list of hypotheses to solve for that. The reason that I need to give it some point is, for example, if you take a look at the first example in the documentation, you see in GeometricScene, you have ABC, and the planar angle is 30 for angle ABC. So if you give the random instance, because there are many triangles satisfying this condition, it actually, the triangle can point to everywhere. So I give it some point, some constraints so that it just looks like the configuration on a textbook. You know, I have a base is like kind of parallel to the x direction, and C is point either up or down. It's based on the chirality of the or clockwiseness of this configuration, but I don't have to specify here. But if you do that multiple times, it definitely sometimes you will see C points downward, and or yeah, you can just choose random instance multiple times. But if you don't like it, you need a specified configuration. So you can just give it a random seed. For example, in options, you go to random seed. It will give you a specific configuration that you can repeat every time. So that's a very convenient way to fix a configuration that happens to you know, meet your visualization requirement. So yes, this is like you solve for the GeometricScene. And what's the length of AY is simply computed by this way. So this is a Euclidean distance AY, so you need to know AY. But A and Y are symbols here. It's not given any values. So you can just grab the value, the numerical values of all the coordinates with the points attributes of the GeometricScene object. So this thing itself is not graphics. It's a GeometricScene object. So it contains attribute points. So you can just evaluate that. It will give you a list of things just look like this. So it's the numerical result. and then it will automatically replace the symbols inside Euclidean distance and give you the result. Okay, so the rationalized thing is that usually, in this type of problem, the numerical values are kind of small. It's usually between 0 and 99. So I can safely just rationalize it, and I assume this is the exact value of this AY I'm going to solve. Okay. Let's see the next problem. This is a problem also found on math competition in Kazakhstan. Zhotkov is supposed to be a Kazakhstan mathematician, and his name is kind of famous over there, and they named a math Olympiad based on the surname of this mathematician. The problem states like this: a point is the endpoint. The point M is the midpoint of side AC and of the triangle ABC, and the point D on the side of BC is such that BMA equal to DMC. And it turns out that CD plus DM equal to BM. And prove that we have this, the sum of these two angles equal to a given angle. So this type of problem also include, kind of constraint that it's hard to come up with compass and the straight edge method. Because, of course, if you go through all the proof and you realize, oh, okay, that's, you do that reversely if you know the result, and that's a different story. But in the problem, usually we have to do that in the forward manner. So the same thing is using the geometric scene, and I've given point 2 coordinates. So because there is no specification of the length of the side of triangle, I just give it usually 2 or 3. It's an easy number to find. And this makes sure AC is on the x-axis and y is pointing somewhere vertically. So, and then I need to specify D, N are the unknown points because their coordinates are not given explicitly, just like B. So I don't put anything behind them. And then I draw a triangle, ABC, and in which M is the midpoint of AC. And line BDC is because the D, there's 2 ways to do that. One is you do D is element of line AC, of line BC, or BDC is like a collinear thing you can write directly. This would basically draw another line, so sort of covering BC, but that's not a big problem. And then you need to specify the equality of the angles. This is a planar angle, BMA, just read it like that. And planar angle is DMC, is this one, okay. Then I have the equality of the sum of segments to another, the length of the other segment. So this just looks like the problem itself. So it's really not programming or just coding, just the translation part. So you have everything set up and give it a random instance. So this is the power of this kind of configuration, because absolutely, if you take a look at this configuration and then take a look at the diagram, you probably need to feel like this is slightly different from this one, because in this problem you specify the length and the perpendicular condition here that everything you can draw is a configuration congruent to this one. But in this one, apparently, if you think about it, you twist the angle here, it probably looks a little bit different. So this is a sort of random instance thing. I feel like it inspires, the solver, the contester or the learner of this problem to, I think, a lot deeper than the simple drawing process of the problem. So yes, so now you have the basic configuration. But if you look at this problem and look at these conditions, probably you might have a rough idea about how to prove this thing. So because I have dm plus cd, so this line or the sum is same as bn. It looks like if I extended MD to somewhere, and then somewhere E and DE equals DC, I might have something to transfer the angles and the equality of the length segments and length dimensions. So this is something I can do, just add some lines in the problem to make it sort of like auxiliary lines in the real proof sequence. You do that with a paper and pencil. So you just do that and specify like BM. It is BM. So this basically, if you add BM, it creates a triangle here. In this one, I actually don't have the triangle here. Just if the dashed line comes from the planar angle function. And then if you create this geometric scene with the same setup, just add a point E. It creates a nice diagram with auxiliary lines here. The other powerful feature for GeometricScene is there's a function that you can wrap it with that. So this gives you some of the critical ideas that you can they can help you to prove the problem. So here is once you have the triangles, it automatically give you some conjectures. These two are congruent, so which is the key point of the proof. And the other one is sort of this, the planar angle transformation. So this is like angle tracing that basically transfer ABM and BEC and DCE to a setup that is actually showing the based on the congruence. So BAM transfer to ECM, and DCM is basically sitting there, but this angle transferred through the isosceles triangle of DEC, and then you have the sum of this angle plus this angle equal to this angle. So ECM, and the ECM is exactly DAM. So I also have uploaded the file to the file section in Pathable, so you can download that to review the procedure of the proof. And also, the feature I like a lot is the HatchFilling. So this gives me a very nice way to highlight the isosceles triangle that I'm going to show in my proof. So this is actually a very, very nice feature that introduced after version 12. I think there's a lot of way to use this feature, but in Euclidean geometry, I feel like this is great. Sometimes if I have, for example, a lot of triangles or a lot of circles, I'm going to show the congruence or concyclic properties. This way to highlight individual components is very useful. It won't give you like confusion if you draw too many lines. And this also, I would say, colorblind friendliness. You don't really need to use 20 colors in a diagram to highlight something. So this is something I feel like if you use HatchFilling, if you work with Euclidean geometries, you can use this HatchFilling to help visualization a lot. Okay. The third problem is also like very cute. It's a problem got many views. I've shown on Michael Penn's channel with 80K. This is an Italian MO problem. So their hexagon has all its angles equal, and the length of 4 consecutive sides are 5, 3, 7, 6, 7, respectively. Find the length of the remaining 2 edges. So this is also very hard to draw directly, this type of problem. But in our case, it's still can be done with this very, very straightforward way to verbally describe the situation in Wolfram language. So first, I would say is that we need to use a property that all the sum of all interior angles in a convex hexagon is 720. So this is something very well documented in Wolfram language and typically in Wolfram alpha. So if you type a double equal sign in a cell, it gives you the spiky thing, and then you type a hexagon. It gives you the some basic information about that, and you can just check the properties. If you want the part itself, just like myself, you can just click the plus sign in the formatted part. It will give you a code look like this, and you can extract the property from the from the Wolfram Alpha pod list. So, and then using that, I can just quickly say I have you know, a list of equalities I can express in terms of a planar angle, and everything should be equal to 720 divided by 6. That's 120 degrees, which is 2/3 of a pi. So this is for the angles. You can just write, you know, the planar angle equal to this, this one equal to this. So I just combine something and make it look neater. And then you're given the conditions for Euclidean distance to satisfy the length requirements. So it's just like this. And then I need to add geometric assertions here because I want to, you know, you can definitely flip F2 somewhere so it does not require, it does not satisfy convexity requirement. So I just put it here, just make sure everything is sitting on the right order so the hexagon is convex. So yeah, you can just put everything inside, and now this is just the configuration in the problem. And then you just need to grab the points and find the exact coordinates. So I just put a utility function in the notebook. It will give you, it is useful to prove this result. So the proof is rather straightforward. You just need to extend the side, and then it meets the segments will meet at the vertices of a larger equilateral triangle. So and then you can just assume some of the length is unknown and use very simple algebras to find the required length symbolically. This gives you accurate result. It's not the numeric approximation. So you can just review the notebook or follow Michael Penn's video to see how it is proved. Okay. Let's see the next one. The excenters and orthogonal triangles. So this part is I do not use GeometricScene. It's something I can compare to the former example. So in this case, I'm going to show how to use a triangle center with the manipulate. So this will give you very powerful way to generate some very sophisticated configurations involve large circles and weird centers. So this one, for example, I give a coordinate of a triangle, 3 vertices, A, B, C. And then the code is actually very straightforward. So this basically extract the coordinates. I use associations, kind of popular to do that after version 11. And then the code is actually very short. It's just you know, repeating itself. You can see that it's the same thing. It's a triangle center given the 3 vertices, and I want to extract the excenter, which is the intersection of or 3 bisectors. One's for interior angle, and 2 for exterior angle. So this is something you can just compute it directly from triangle center, and you do that for all the 3 vertices. And this is for if you have the coordinates of the 3 excenters, and then you find the orthocenters. So it's just the orthocenter of a larger triangle. So what the configuration says is the triangle formed by 3 excenters, and you have a smaller triangle, and you find an incenter. So the orthocenter of the largest triangle is the same thing as the incenter of the smaller triangle. This is a very classical example of how the excenter and other centers working together. And if you want to create animation from that, it's kind of same as the code above, but I just use the triangle construct. The other thing is basically I want to extend the side of the segments to infinity for each side of the smaller triangle. And then I have the repeating the sides and the triangle construct, because I want not only the center, but also the X circle. So the circle that tangent to two sides, all the three sides, and the sitting outside. So the same thing applies to these lines that connecting the excenters. And eventually I want to name the controllers as the ABCs. So this is basically I want to put up the decorate the controllers. So this code looks a little bit longer than before, but it's just a repeat itself and easy to share because it's just text description of the problem. And then this is a syntax for locator. If you refer to manipulate a documentation, it's just a template. Once you just need to do that once. And then I just change the appearance of the points to B and to C so that it looks very nice in the animation. Okay. It gives you the very smooth motion of the points and how the concurrency is invariant based on the changing position of ABC. So it's very nice. And this method is usually much faster than the GeometricScene because it does not involve anything like equation solving. It just directly computes a real-time computing of all the centers and intersections. So this is a very powerful way to generate such sophisticated configuration with a minimum delay. Okay, let's take a look at the last example. It's a very interesting one from Sharygin 2016. It's an altitude AH of a triangle ABC bisects a median BM. Prove that the medians of a triangle ABM are side length of a right triangle. So this problem is a little bit tricky, and you can just review that in depth with the file you have. You can download it from Pathable. So this problem is kind of tricky because usually the triangle you draw, and you draw the AH, and it usually does not bisect BM. BM is like this one, so it's the median. It's median line. It's connection of vertex and the midpoint of opposite segments. So in general, say if you draw it, it won't intersect exactly the midpoint. So there is something very special about this triangle, and you can use the same thing. This to actually explore it. Typically, I just use a triangle center here. Triangle center not only gives you the actual center, but also gives you some important points like the foot of altitude. So this is basically like the same thing as the problem. It's just really like BM is the midpoint of AC, N is the midpoint of BM. And in this point, because AH bisects BM, it means the midpoint of BM is collinear with AD. So this is basically the setup, okay? And then you can just find a random instance for this configuration, and it's not unique. So you can have two ways to prove that thing. Is one is use a very algebraic way to handle that. The other is very nice feature is the demonstration project. Probably you know that for a long time. You have tons of good examples, and typically if I'm going to introduce a new theorem in my presentation of Planar, I just call such a easy API, and it's from source, copy resource project. It basically to generate this code for you, and then you run the shift enter in notebook, and it'll give you the demonstration here. You can play around, and this is a more generic way to prove this problem. and it gives you, based on Menelaus theorem, it's very dynamic, and it's zero length of code, you just download it. And then it will show you how to use that in different two configurations in the problems, and you can find the proper way to compute the special property of the point D on segment BC. So yeah, so once you have that, everything else is based on the proportionality of triangle similarities. It's basically, if you have triangle and it's cut by a segment that's parallel to one of its side. So you now have some line segments in which their lengths are proportional. So that's very fundamental thing in triangle similarities. So you can use that to prove this problem and do some basic computation. And the last part I'm going to show is how you integrate the graphics with the current graphics system with the show. So you have a GeometricScene, and its graphics can be extracted, and you put them in the show. So this gives you a sort of a wordless proof to the problem. So it's very nice. So eventually you want to prove is all the three lines that forming red triangle is exactly EKB. So if you do the computation, you will find there are two parallelograms in the problem. So it basically transfer one median MF to KB and the other median AN to EK. So it happens that if D is the like 1/3 point of BC and D is the midpoint of DC, KD is exactly a quarter length of CD. So you can just do that by algebra, and exactly the same thing for AE. So you transfer the AN to EK. So eventually the triangle you are going to look at is EKB. Or if you want to do that before you find out the result, you can just use sort of brute force way to compute the Euclidean distance of the three medians in A and B, this small triangle, and compute that with just one line, and you find the first one plus second one equal to third one. So it's Pythagorean properties. So that's something you can. I feel like this Wolfram language in this part bridges algebra and the geometry nicely. So it's very powerful, and I just use that to solve the problems online, and feel it's very smooth experience to handle everything. Okay, so yeah, let's conclude everything in the talk. One is the GeometricScene follows the statement problem. You have seen that it's just a dual translation, and triangle construct or triangle centers is just a very powerful functions to give the instance access to all the important segments, and you can find the properties or attributes in the documentation center. That's very nice.
Shen, sorry, I didn't want to interrupt, but our session will end automatically in a little under 30 seconds.
Okay. Yeah, so this is the last part. I'm going to talk. Yes. I think that's everything I have covered in the talk. Thanks for attending.
Thank you all for coming.